In this video, we're going to take a look at an example, and we're going to use the equation and some of those values for our semiconductors that we saw at the end of our previous video. As always with the examples, I would encourage you to pause the video and try to work it out, or at least set up the problem by yourself before watching me work through it. So for this example, what we want to do is calculate the intrinsic carrier concentrations, and so remember that's N sub I, for silicon and germanium at room temperature. And so throughout this class, what we're going to assume is that room temperature is a temperature of 300 Kelvin. And so that's a little bit warm. That corresponds to about 80 degrees Fahrenheit. So in some other places or other text, you might see different values such as 290 Kelvin, but 300 is of course just a nice round number to work with. So let's start by looking at our Ni for silicon. So for silicon, we are just going to go to that equation we had. So our N sub I is equal to, we have our B value, which was a constant. And so from our previous video, we had that this was 5.23 times 10 to the 15th. And the units on that are per cubic centimeter, Kelvin to the minus 1.5. That's multiplied by our temperature, which was 300 Kelvin to the power of 1.5. And now we have the exponential of, and then in the argument of our exponential, we're going to have a fraction. In the numerator, we have our negative of our band gap, so we have negative 1.1 EV for silicon. And in the denominator, we have 2 times our Boltzmann constant times our temperature. Now, since I'm using EV for my band gap energy, I'm going to choose to use the Boltzmann constant value that has EV as well. So that was 8.6 times 10 to the minus 5th EV per Kelvin. And remember, there was another value that was in joules per Kelvin, but in this case we want it in EV, so that will cancel out. And then our temperature, again, we're assuming room temp, which is approximately 300 Kelvin. And so just real briefly, at least this first time, we can see our units canceling out. So we have this K to the negative 1.5 is going to cancel out with the K to the 1.5 here. In the argument of our exponential, we want that to be dimensionless. And we see we have EV canceling out with EV and Kelvin canceling out with Kelvin, as we would expect. So if we plug in these values, we get that the intrinsic carrier concentration for silicon is approximately 1.50 times 10 to the power of 10th per cubic centimeter. Now, I'll mention a couple sort of assumptions that we're making after we do intrinsic carrier concentration for germanium, but let's just say for now that we could be a little more detailed in how we calculate this, and in some text or some references you might see a number slightly different from this, but this is a pretty good approximation. And just to kind of put it into perspective, I'll throw this number out in a later video as well, but our density of our silicon atoms, so density of silicon is on the order of 10 to the 22 per cubic centimeter. And so a good way to sort of visualize this is if we had a cube that was 1 centimeter sides, we'd have roughly 10 to the 22nd silicon atoms in that cube. In that same cube, we would have about 10 to the 10th free electrons and free holes. And so of course what we can see is that we have far fewer free electrons and free holes in room temperature for silicon. Again, that's just to kind of put these numbers into perspective, because sometimes with these really large numbers, it can be difficult to sort of get a hand on that. Okay, so now let's switch gears and look at germanium. So again, we're going to plug into that same equation for Ni. So our B for germanium is different because remember that's a material property. So 1.66 times 10 to the 15th is what we had in our previous video. Units are per cubic centimeter, Kelvin to the negative 1.5. And again, we have our temperature, which is 300 Kelvin, raised to the 1.5, exponential, and then in the argument of our exponential, we have negative of our band gap, 0.66 EV in the numerator, 2 times our Boltzmann constant, 8.6 times 10 to the minus 5 EV per Kelvin, times our temperature, which is 300 Kelvin, and plugging all that in. So our units, of course, are going to work out the same way it did for our silicon. and we get that our Ni for germanium is approximately equal to 2.40 times 10 to the 13th cubic centimeter. So if we're looking at 1 cubic centimeter of silicon, we have on the order of 10 to the 10th free electrons and free holes. If we're looking at a cubic centimeter of germanium, we have on the order of 10 to the 13th free electrons and free holes. So what we can do is we can consider that band gap energy. So let's say considering our band gap energy Eg of our two materials, which is our 1.1 and our 0.6, so those were the negative of the band gaps. Does it make sense that we have our free electron and free hole concentration higher for our germanium? And so of course the answer is yes, it should make sense. And if we think about it in terms of our band gap, so let's say our silicon maybe looks something like this. So if this is our silicon here, our germanium would be about half that size. So we'd have germanium here. And so what that should indicate to you is that we need smaller amount of energy, because down here is our valence band, which is full of electrons. So we need a smaller amount of energy for this electron to come up here into our conduction band. And once it comes up here to our conduction band, it's contributing to this number here. Whereas for silicon, we have a larger band gap. So these are both our EGs. And we need more energy to get an electron up here to the conduction band. And so what that means is for the same temperature, which means the same amount of energy on average for all of these electrons in our valence bands, we're going to have more electrons in our germanium conduction band than we are in our silicon conduction band. So one other quick note, I mentioned a little bit earlier that we were kind of making some assumptions. For this class, that's going to be fine, but I just want to at least point those out so that you're aware of them. So we're assuming that our band gap and that constant B are independent of temperature. And so it turns out that's not entirely true, but again, for this class, we're going to assume that that's a good enough approximation. And of course, we're not really going to worry too much about the semiconductor physics. We're just introducing this so we can have a better understanding of how devices are actually working. In our next videos, we're going to look at what happens when we dope our semiconductor, and then finally we're going to get into a simple semiconductor device.